So welcome back. In our previous class we were discussing about limits of a function. Limit was actually the concept that where does a function tend as the independent variable is supposed to move towards a point. Right, in the case of single variable functions. Now let's discuss about continuity of a function. Continuity. So in layman's meaning or in general, continuity can be vaguely defined as follows. Suppose we have a function f, and if we can draw the graph of the function f without lifting your pen or pencil or whatever from the paper, that means suppose this is a Cartesian plane and we are trying to draw down the graph of a function. So if you start at a point and you can finish drawing the graph of the function without lifting your pen or pencil from the paper, such functions are called continuous functions. See, the graph of a function need not be like this always. There can be graphs of functions like this one. Right. See, this is a little slanted. This has to be. Functions can be like this. Or there can be functions of this form. This circle means the function is not, it's a hole in the graph. Right. So such a circle, an empty circle in the graph means there's a hole in the graph and we call it hole itself. Perfect. So the vague definition of continuity is as we have discussed now. If you can draw the graph of the function f without lifting our pen or pencil from the paper, such functions are said to be continuous. But there are still ambiguities around. Mathematically, we cannot define continuity like this. This is a much more literal mode of defining continuity. We have a much more algebraic way to define and work with continuity, and let's examine that. So the mathematical definition of continuity of a function, we use the idea of limits. So suppose we have a function f, right, and choose a point a or a function f of x and a point a in the domain of f. Okay, so the function f is said to be continuous at this point a if it holds three properties. The property number 1, f is defined at x equal to a. See, continuity requires mere definition of functions or the definition of function at that particular point. That's obvious. We cannot even say anything about a function if it is not defined somewhere. Right. The second property is limit x tends to a, f of x exists. When we discussed about limits, we have seen that, or we have discussed that the limit need not be existing always. Right. But to be special, if a function needs to be continuous at a particular point, the function has need to have a limit at that point, right? And the third property is limit x tends to a, f of x equal to f of a. This is the most pivotal property or the pivotal part of definition of continuity. This says that the function has a limit at a and that limit is absolutely equal to or it is equal to the value of the function at a. In other words, the limit of the function f at a coincide with the value of the function of f or the value of the function f at a. Right. So these are the three aspects of testing continuity. In fact, the function has to be defined at the point. The function should have a limit at that particular point, and that limit and the value of the function has to be equal. Right. This definition will be used to test for continuity. The other one is not that easy, right? Of that graphs, we may need to draw down the graph of every function, and it is not a logically valid argument as well. So let's go to an example now. Before example, prior to going to examples, let's examine a few properties of continuous functions. So property number 1, all polynomial functions are continuous. All polynomial functions are continuous. Second one, all rational functions are continuous. You know what is a polynomial function and a rational function. We have discussed these terms when we had our lecture on limits, I think. So all rational functions are continuous, but we need to add something here, are continuous wherever it is defined. See, polynomial functions will be defined everywhere, but a rational function will be of the form, say, some g of x by h of x. But this need not be defined everywhere. This is not defined especially at those points where h of x is 0. So this makes sense when only when if h of x is non-zero, and by this statement we mean that the function is defined at the particular point where we test for continuity. Right. Okay. So remember these two, and analogous to the rules of limits or the properties of limits, we have a few here. Suppose f of x and g of x are continuous functions, and they are continuous at x equal to a. Suppose f of x and g of x are continuous at x equal to a. Then f of x plus g of x is continuous. F of x minus g of x is continuous. F of x into g of x is continuous. F of x by g of x is continuous whenever g of x is non-zero. Nth root of f of x is continuous wherever nth root of f of x is defined. See, the root function is somewhere special. It need not be defined everywhere as a real number. We know that what's inside the root determines the value, and we haven't seen any real number any real number which is the root of a negative number, right? So this has to be specially mentioned here, is continuous wherever defined. Probably every property is listed here except the last one is actually familiar to you from the part of limits. We have seen that the definition of continuity, the mathematical definition of continuity itself make use of limits extensively, and using that you can just you can prove this all if you want to, or let's fix it for an assignment. Right. So now let's go to an example. We don't visit any example where we use graphs to determine the continuity. It's a hell lot of job. So we move to the algebraic part directly. Consider the function f of x equal to x square minus x square minus 5 is x square minus 5. Determine whether f of x equal to x square minus 5 is continuous at x equal to minus 3. So we have a function f of x equal to a here, and we need to check the continuity as a function x equal to a, as we have discussed before, and a is minus 3 here. Right. So remember, what were the three parts of continuity? First one was the function has to be defined at that particular point. So here the particular point is minus 3. So f of minus 3 has to be well defined as a real number. Let's examine what is f of minus 3. So f of minus 3 is f of x equal to x square minus 5. So f of minus 3 has to be minus 3 whole square minus 5, which is 9 minus 5, 4, which is a well defined real number. Right, so the first property holds. Now the second part, the limit of f of x has to be existing at x equal to minus 3. Or in other words, limit x tends to minus 3, f of x should exist as a real number. Right, so when we discussed about limits, in the properties part, we have seen that if f of x is a polynomial function, then limit x tends to a, f of x is nothing but f of a. Right, here x square minus 5 is a polynomial function in x, and for that reason limit x tends to minus 3, f of x has to be f of minus 3, and that itself gives the fact that the function is continuous. But let's go on the track. So f of x equal to f of minus 3, which is 9 minus will be minus 3 square minus 5 will be 9 minus 5, which is 4. And from this analysis we can conclude that limit x tends to minus 3, f of x equal to f of minus 3, which is in fact the third part of the test for continuity. The limit at the particular point coincides with the function's value at that point. Right, so f of x equal to x square minus 5 satisfies all three aspects of testing continuity. The first one is satisfied, second one again the limit exists, and third one the limit actually has the value of function at that particular point, satisfies all these three criteria, and for that reason we regard f of x equal to x square plus x square minus 5 as a continuous function at x equal to minus 3. Right, remember we emphasize the fact that this is continuous at x equal to minus 3, that we don't know, every function need not be continuous everywhere. There can be some functions which are continuous somewhere and discontinuous somewhere, and in fact there are functions which are discontinuous everywhere, which are not even continuous at a single point. There are such functions as well. So don't ever think that all functions are continuous everywhere, or at least some points need not be. There are functions which are continuous anywhere or nowhere. Okay, so this is about testing continuity. Now about the slope of a curvilinear function. Slope of a curvilinear function. So what is a curvilinear function? Or simply a curve. See, we have seen functions and we have evaluated the slopes of linear functions. Right. How did we do that? We found 2 points, say x1, y1, or x1, y1 here, the first one point, this is x2, y2. Then we found the slope as slope is equal to y2 minus y1 by x2 minus x1. And using this slope we had made an attempt to write an equation for the straight line as well. So what happens if we don't have a linear function but instead we have a curve like this? Suppose, see, the graph of a function need not be a straight line always. It can be a curve if it is a non-linear function. We have seen that the graph of parabola appears to, the graph of a quadratic function appears to be parabolas. Right. So in that case it's possible to have a curve instead of a straight line as a graph of function. In that case, how will we find the slope? Right. So the slope at this point, say, let this be P. How do we find the slope of this curve at this point P? The slope of the curve at the point P is defined as, see, I'll just replace P to somewhere here for the sake of comfortness. So the slope of the curve at the point P is defined as the slope of the tangent line at P. You know what is a tangent line? The tangent line is a line that touches the graph exactly once, not again, exactly once. So suppose this is a tangent line at the point P, this is the tangent line at the point P. The slope of the curve is defined as the slope of the tangent line at P. Right. So at any point we can construct a tangent line, and the slope of curve at that particular point is defined as the slope of the tangent line. Now we know how to find the slope of a tangent line, since tangent line is a straight line. But since we don't have any information about the tangent line, this makes again a little more complicated to find the slope of the tangent line algebraically. Here we make use of a technique. Right. So we have a point P here. Suppose I choose a point Q here. Let it be capital. Points are mostly not using capital symbols. For the sake of comfortness, I choose Q to be maybe here itself. And the curve is a little more curved. Okay. Here I construct a new line which passes through P and Q. Which passes through P and Q. That means this line, I call this as L1 or this as L2, and this line L2 passes through two different points of the curve. Two different points of the curve, and such lines are called secant lines. Such lines are called secant lines. So we have heard two terms here, tangent lines and secant lines. So what are tangent lines? Tangent lines meet the graph only once. Right. The secant lines will meet the graph twice. They will have intersections with the graph twice, and this will have exactly one unique intersection with the graph. Perfect. So I'll just redraw this setup a little more magnified. Suppose this is our graph for now, and I choose this to be P and this to be Q. I'll make it a little more slanted. See, I'm very bad at drawing graphs. Say this is P, this is Q. So for now, let this be the tangent line at P. Assume that this is the tangent line at P, and this is the secant line. This is the secant line passing through P and Q. I call it S, and this is L or T, the tangent line T. Okay. So obviously this will have coordinates. Let this be x, y, and this say right, x1, y1 maybe, and this is x2, y2. Right. Now we have 2 points through which the secant line passes. Right. Then we can find the slope immediately, since we have the 2-point formula, as the slope of the secant line S is y2 minus y1 by x2 minus x1. Right. Now we make a small arrangement that we bring the point Q nearer to P. We bring the point Q nearer to P on the graph. Right. So the Q will be shifting from here to very next point here, maybe, or very similar, maybe next time here, and this will come arbitrarily close to P. Right, arbitrarily close to P, and for that case we choose the coordinates of the new point Q as x plus delta x, and say this is the function of graph, so the other point is f of x plus delta x. See, this y is nothing but f of x, right? Since this is the graph of the function f. So the new point q will be designated as x plus delta x, f of x plus delta x, since the x coordinate of the new point q is actually obtained by moving a very little quantity, and that is delta x. Right. Delta x is a very small quantity, which in turn means p and q are very much nearer. And moreover, as p and q comes closer and closer, the secant line will come closer to the tangent line. Right. And once they meet, the secant line will be exactly the tangent line. Perfect. So as we come closer to P, the secant line will be approaching the tangent line, and once they meet, the secant line and tangent line will coincide. Alright. So what do we mean by P and Q are meeting? The difference in their x coordinate has to be 0. Right, which means delta x has to go to 0. Keep that in mind. And now let's try to write an expression for the slope of tangent line. The new 2 points of the secant line are x f of x and x plus delta x, x f of x plus delta x. Then we can write the equation for tangent line or the slope of secant line as f of x plus delta x. I hope you remember this expression from the previous part of slopes. F of x plus delta x minus f of x divided by x plus delta x minus x, which is x plus delta x minus x is delta x. Okay, so this is the slope of the secant line passing through P and Q, and we have seen that as P and Q comes closer and closer, very much closer, the secant line will approach the tangent line. So P and Q are very much closer means their difference is actually very small. The difference here is delta x. So delta x, if delta x is very small, the secant line will eventually comes closer to the tangent line. Right. So this is the expression for slope of secant line, and from this we can find the expression for tangent line as, let me clear this for now. Slope of tangent line as, see what I am doing here, limit delta x tends to 0, f of x plus delta x minus f of x by delta x. See, I've made delta x tending to 0, which means the difference between P and Q are now tending to 0, means getting very smaller, and then the secant line will be approaching the tangent line, and this is actually the expression for secant line. As the secant line approaches tangent line, the expression for slope of secant line will give us the expression for slope of tangent line. Exactly. So this is the expression used to find the slope of the tangent line, slope of the tangent line at the point P. And this slope is actually defined as the slope of the curve itself. So what we discussed now, the slope of a curve at any point is defined as the slope of the tangent line through that point, and the slope of the tangent line can be found using the secant line, and this is the expression to find the slope of a tangent line.